In this video, we're going to continue with our Calculus 1 final exam review, and we're now switching to the calculator permitted portion of the test. Now, for question number 8, we're provided with a table of data whose inputs are given to us in the top row and the outputs in the bottom row. We would like to use that information to determine or estimate a function's derivative at the points down below. Now, there are lots of ways to predict or estimate a derivative, especially derivative values given inputs. We could try to do some curve fitting or find the equation that represents these data points. But what I would recommend, since these x values for the derivatives exist so nicely in between the x values of the function inputs, is I would simply use the notion that a function's derivative is really just a measure of the change in y over the change in x. And while this may not be the precise description of the derivative, it would be a good way to estimate in this case. So when we need to find the derivative at 0.5, well, that happens to be exactly halfway in between these two data points, and I would just easily compute 5.4 minus 5.0. That'll give me my change in y values, and then subtract in the same order 0 minus 1 to give me my change in x values, and this result comes out to be 0.4 divided by negative 1, or negative 0.4. And we can set up the remaining table much the same way. And it looks like our approximate derivatives are changing from negative 0.4 to negative 0.9, negative 1.3, and negative 1.6 for each of these x values. Now again, this is assuming that we have a constant rate of change in between the known x values above, but again, since this is just an estimate, I think this technique is wholly appropriate for this particular question. Now, part B goes on to ask, is the second derivative positive or negative over this interval? And we should explain. Well, recall that the second derivative is a method of measuring the change in the first derivative. So if we investigate each of these derivatives and recognize how these are changing, well, it appears that these derivatives continue to decrease. It's not like they're remaining constant or anything, but they're continuously getting smaller. So I would say something like this, that since the first derivative is decreasing, then our second derivative is negative. And that would be a similar claim to this one here. If we've got a graph of some function, let's say that this line represents f, or f of x, I should say, y equals f of x. If our function is shown to be decreasing, then that implies that f prime is less than 0 or negative. So if a function has decreasing values, then the derivative is negative. If our derivative has decreasing values, then the second derivative is negative. All right, in number 5, we're jumping ahead to integrals, and we would like to use integrals to compute the area of these regions here. Now, the question is specifically talking about area and not accumulated change. If we were talking about accumulated change, then we would simply write an integral from 0 up to I think they're implying that C is this position here. We've got A, B, and C. So from 0 to C, we can write a single integral, and that would represent the total accumulated change. But I think what they're implying here is that we've got an area in this group, and this group, and we should recognize that when written as an integral, this area ends up being negative. It's less than 0, and same thing over here. When written as an integral, this area is going to compute as negative. Now, we are told, in fact, that this area below is 4, so the integral from 0 to a would actually compute to be negative 4 and so on. So I can think of a couple different ways that we would answer this. More commonly, I think or the most common answer, I think, would be something like this. The function is f of x, and so when I integrate f of x with respect to x between 0 and a, I should recognize that that area is going to be negative, or at least this integral is going to calculate out to be negative. So if I negate that negative area, then this result will be reported as positive. To that, I will add the integral from a to b of f of x. Now, this area is already positive, so I'm going to leave that one alone as it is. That's our positive area. And then lastly, I think I would negate this area, so I can add a negative result or simply subtract the area from b to c. And this is written again with f of x, the function f of x with respect to d of x, or to d. The function f of x with respect to x. And I think that would be a fine answer for this particular question. Another way to negate area and to avoid these negative symbols is to reverse the order of our boundaries on our integrals. So if I integrate not from 0 to a, but from a to 0 in reverse order, then that too will negate our result. So we could say from a to 0 of f of x plus a to b of f of x plus the integral from c to b of f of x. Because we should recall that not only do areas below the x-axis represent negative areas, but also when we integrate from right to left, that's essentially going to compute negative areas. Because we use this phrase from time to time, accumulated change. And if you think about it, the results are accumulated as we increase. A lot of times our x-axis represents something like time, whereas time is positive, or if we increase our x variable, we introduce or increase the total amount of accumulated change. But if we were to measure in reverse, if time were possible to go in reverse, let's say, then as we go from right to left, the area that we accumulate ends up being negative because we're not accumulating it anymore, but we're actually removing the area as we calculate from right to left. And so that's why reversing the boundaries of integration or limits of integration serve as a way to negate physical area. Okay, and moving on to this one, there's a bit of missing information that was supposed to be supplied here. We have the function f of t that represents this, what I sometimes call him a curve, but this function here, this f of t is the function that we see here. There's a secondary function that we should be aware of too, and that's g of x. Now, g based on x is the result of the integral, in this case from 0 to x of f of t dt. So this phrasing should look familiar. This is our fundamental theorem of calculus part 1. And if you recall, what we're saying is that this new function g of x is dependent upon the area that's calculated based on the function f on the right-hand side, starting at position 0. And so the question goes on to ask us to evaluate g at -1. Well, I'll just go ahead and calculate it here so that it's all in one window. But g evaluated at -1 would be the integral from 0 to -1 of f of t dt. And so we're essentially trying to calculate the area in this region starting from this position here at 0 and going towards this position here at -1. So if we're evaluating that, g at -1, we don't know what the function f of t is, so it's not like we're going to evaluate this definite integral using any sort of traditional calculus. We simply need to calculate the area. Now, we've got to be careful though too, because the lower boundary is fixed at 0. The upper boundary is the variable here is x. So we are traveling from 0 to -1. That ends up being right to left. This area should be calculated as a negative result. But since this is a triangle, we'll go ahead and calculate the area as 1/2 times base times height. And we just have to remind ourselves that since we are traveling from right to left, this answer should be negative. And so I would say that g at -1 is -1/2 times 1 times 2, or simply -1. For g of 4, now again, we're calculating g at 4, which would be the integral from 0 to 4 of f of t with respect to t. So we're not talking about this triangle anymore, but starting at 0 and traveling out to 4. And again, the labeling on this particular graph is poor. My apologies for that. But that is talking about this triangle over here when we go from 0 to 4 on the t-axis. And so g of 4 would then be 1/2 times the base times the height. And this area is going to calculate as positive because we are accumulating change from left to right. And it appears that this area comes out to be 4. G at -4, calculated much the same way, is going to be the area from 0 to -4. Now this time we've got this triangle that we just calculated a minute ago to be -1, at least when we start from 0. And then we need the area of this trapezoid. Now what's interesting is this trapezoid is below the x-axis, so it would normally be calculated as a negative result. But since we're calculating from right to left, this should be calculated in the opposite of that. So we're actually going to compute a positive area. So just to show it all, we'll have -1/2 times 1 times 2. That's a good way to calculate the triangle. Plus the area of the trapezoid. Now the trapezoid's area is the average of the bases. So this base is 3, and this base down here is 1. So that's 3 plus 1 divided by 2 times the height of the trapezoid. And this height is 2. So again, we said that the area of our first triangle was -1. Our math supports that again. The area of our trapezoid is going to be 4 square units, and it does need to be positive. And the sum of -1 plus 4 is 3. So g evaluated at -4 is 3. Now, answering part B, this is where it gets kind of interesting because we're being asked to calculate the rate of change of the area function at the location 0. So this could be kind of tricky if we're not aware of what's truly happening. But g of x is not the equation of this curve here. And so it's not asking for the derivative of this curve per se, or not derivative of, so it's not the derivative of this corner, which can't be found. It's the derivative or the rate of change of our area function. As we're accumulating area as we move from left to right, our area is getting larger and larger and larger. And the area actually continues to get larger as we move left to right still, because we're still accumulating more area. Our change is increasing. But let's recall that our fundamental theorem of calculus says something that allows us to account for this very, very nicely. And I actually jumped back to our Unit 5, Part 2, Lesson 4 notes. This is Unit 5, Part 2, Lesson 4. This is where we actually shared the fundamental theorem of calculus, Part 1. And it states that if an area function is written as a definite integral from some fixed starting point to a varying end point of a function with respect to t, they use the letter t here, then it stands to reason that the derivative of the area function, which is the derivative of this integral, simply is that function evaluated at the upper boundary x. And so that seems kind of weird to describe at first, but perhaps you start to see that this derivative with respect to x um, essentially works against the antiderivative notation here. And since it's x, this boundary that acts as our variable, then the accumulated change at a single position, so at a single, say, height of the function itself, is simply that function evaluated at the letter x. So I'll try to say it another way by looking at this particular graph here. Again, we've got accumulated change that's occurring. So if we think about all of these infinitely narrow rectangles that are representing area that we are accumulating as we move from left to right, if I want to know at one instant what the area is changing as, at say time 1, for example, how much is the area changing at that particular instant? Well, the area is simply changing by the height of that rectangle. And at another instant, again, we're accumulating change, so all of these areas are being accumulated. But at another instant, let's say at 2, the amount of area that's being accumulated at that specific instant is just this area associated with this infinitely narrow rectangle. So when we're being asked to evaluate g prime at 0, well, again, g prime at 0, well, let's say it this way. G prime of x is equal to the derivative with respect to x of the integral from 0 to x of f of t dt, and that by definition is equal to f of x. So when evaluating g prime at 0, then all we need to do is evaluate f at 0. So the height of this rectangle at this specific instant is the accumulated change at that specific instant. And so the height of that particular rectangle is 2 at this moment. So the change in the area function at that particular moment is simply 2 units. And if we're thinking about the derivative of the accumulated change as being the height of the function, then we might be able to answer question C. Now, if we start at 0, where our lower boundary exists, and moves to the right, the area that we compute, at least in this window, is constantly increasing. So again, as we move from left to right on the t-axis, our area is increasing. It's kind of like saying that our g function is increasing on that right-hand side. But again, with 0 being our starting point of this graph, as we move to the left, it looks as though area is increasing, but again, our lower boundary starts at 0. So as we move to the left, our accumulated change begins to decrease. And so relative to the point 0, I think we've reached a local maximum, because again, our accumulated change is starting to decrease when we move from right to left. And this may seem counterintuitive or going against the fundamental theorem of calculus, because this is again supposed to represent accumulated change. But what we have to recall or remember is that the way the definition of the fundamental theorem of calculus was written was that x has to exist between a and b. So x is larger than a or equal to a, and it's less than or equal to b. In this weird case here, our upper boundary happens to be less than our lower boundary, and so that affects our accumulated change just slightly here. So again, as we're moving left, we're starting to see a decrease in total area. So again, I would, for that reason, say that a local maximum exists at x equals 0. And then by the same token, as we continue to move to the left from 0, while this area is considered negative, let's use a different color to make that stand out. If I can select a different color here. This area was considered negative, then this area is considered positive. As we make that transition from negative area to positive area, we start accumulating more area when we move further to the left. Well, we've now transitioned from a decreasing function to an increasing function, and that implies a local minimum. And so at x equals -1, I think we've got a local minimum. And I believe that's going to be all, because when we're talking about area, even though this function starts to decrease or increase back towards the x-axis here, the area that's being accumulated continues to increase. We're still gathering more area as we move from left to right. So since area continues to increase, I don't think we're going to reach another maximum or minimum point in this particular window. And to answer part D, locate the absolute maximum of this particular function. Well, remember the absolute maximum of this function is where on the x-axis are we going to establish the largest area. And we've already broken this apart into pieces. This trapezoid right here has an area of +4. This area has -1, and this area has +4. Oops, and I forgot to note that we're only considering the region from -2 to +4, so we don't even need this full area of the trapezoid. This area of the triangle is what we're after. That area is a +1. So if I'm talking about the accumulated change starting at 0, let's just consider what happens as we move to the left. If I start at 0 and travel to the left, well, there's -1, and then I add to it another 1. The total area accumulated from right to left from 0 to -2, that area ends up equaling 0. These areas above and below tend to negate each other. They cancel each other out. So nowhere between 0 and -2 am I going to find an absolute maximum, because the area ends up being, at the most, 0. As we move to the right, however, the area continues to accumulate all the way until the end of this boundary, because we're being asked to stop here. And when when t is equal to 4, now we have a total area that equals 4 precisely. And so we would say that the maximum, absolute max, is at the boundary t equals 4. And we'd mentioned this in the past, but haven't talked about it much recently. When looking for an absolute maximum, if the absolute maximum is not identified at a local extreme point, either the local max or one of the local maximums within an interval, then we always do need to consider the endpoints. And in this case, that's exactly where the maximum area occurred, at the endpoint on the far right of our interval. So I think this is a good stopping point for this video. We'll continue with the next problems in the next one. Thanks for watching.